All right, good morning, everybody. We are continuing with Unit 7, Differential Equations. Today we are looking at Lesson 4. It looks like Euler's method, but it's Euler's method. This is Euler's method. Students will be able to use Euler's method to approximate a derivative. Think of this as connect the dots a little bit. We draw a point, we have a little line segment, we connect it. We have another point, we draw a little line segment and connect it. So that's what's happening with Euler's method. Now we're not technically drawing those dots and connecting them, but that's what's happening with the values. So I have a formula for you to memorize. Y sub k equals y sub k minus 1 plus h times f evaluated at, x of k minus 1 and y of k minus 1. That is a mouthful. A couple notes. This h I have also seen written as delta x, which means the change in the x value. You're finding your new y value, and you're getting your new y value from the old y value. You're multiplying by delta x, and then you're multiplying by the function evaluated at the step before. And this will make sense for us in a few minutes. What it does is it allows us to find the numerical approximation of a function given the derivative. It's a recursive process, meaning each step relies on the step before. You can't skip steps. We check small successive changes in x. The smaller the change in x, the more accurate the approximation. And that makes sense. The smaller the step you take, the better the approximation. So a new notation for a derivative, this y dot. Now in our old textbook, and I know we're not using textbooks this year, I've seen y prime for dy dx, and we know that one. And I've seen y dot mean dy dt, specific to time. So just keep that in mind. Not a big deal, not an AP concept, just new notation to be aware of. So example 1, use Euler's method with a time step delta x equals 0.2 with n equals 4 steps to approximate y dot equals y minus t squared, y of 0 equals 3. Now, two little notation things here, and this is my old typing, I apologize for that. This y dot, if I just told you it meant dt, this should be a delta t instead of a delta x, and this would be dy dt if we're talking about time. Not the end of the world, but I just wanted to be consistent. So you are going to need, without a doubt, your calculator today. Get your calculator. There's no way to do this without. So, excuse me, my initial step is 0. My initial t value is 0, so that's this. My initial y value is 3. Now I'm going to copy in the formula here so that I can see it. Y sub k is equal to y sub k minus 1 plus h f of x k minus 1 y of k minus 1. We have both the x and the y because it doesn't have to be a function. It could be a circle. All right, so how do we do this? Well, my new value, my Euler's method here, this is step 0, step 1, step 2, step 3, and step 4. So that's where the 4 steps come from. That the delta t equals 0.2. So I make a step of 0.2 each time. So my previous y value is 3. H is that delta t. All three of these things kind of mean the same thing. So that's 0.2. And then I have to evaluate the function at the previous x and y values. So my function is y minus t squared. So it's going to be 3 minus 0 squared. Okay, so grab your calculator. 3 times 0.2 plus 3, I've got 3.6. So my new y value is 3.6. And then I do it again. So my next y value is going to be the previous y value, which is 3.6, plus that h, which is that delta x or delta t, depending on the variable, is 0.2. My previous, so I'm going back to the function here. Remember, this is the function. My previous y value was 3.6 minus my t value, which is 0.2 squared. I told you you needed your calculator today. So 3.6 minus 0.2 squared times 0.2 plus 3.6, and I get 4.312. Everybody always wants to know, how many decimal places do we need? Yeah, you need a lot. For the AP exam, we have to be accurate to 3 decimal places, but that's for the final answer. So as you are working through the problem, don't round. Don't round till you get to the very, very end. All right, let's do another one. Pardon me. So this is 4.312 plus 0.2, 4.312 minus 0.4 squared. So let's do this. 4.312, that's still left in my calculator, so I'm going to leave it there, minus 0.4 squared times 0.2 plus 4.312. I get 5.1424. And keep going. 5.1424 plus 0.2, 5.1424 minus 0.6 squared. Okay, so I'm just going to my calculator now, and I get 6.09. So there we go. My dog's barking over there. Euler's method. A lot of, and I hate this expression, but a lot of plug and chug. Substitute values, find new ones. All right, let's try one more example this morning. All right, example 2, use Euler's method with time step delta x equals 0.1 with n equals 6 steps to approximate the following function. I'm going to change the notation on this one. Instead of y dot here, again, I think this is an old typo of mine. I'm going to go with y prime because this is an x. So y prime is dy dx. Oh, excuse me, goodness. So if you go to look up this procedure on other videos, they might not organize it with a table. It's just one way to do it. They just might write the formula out over and over and over again. But my initial values are 0 and 1. Remember, my formula is, I just want to make sure I use the same letters as last time. Y sub k equals y sub k minus 1 plus h f of x k minus 1 y k minus 1. All right. So remember, let's use a different color highlighter. This function is really going back to this, whatever you were given in the problem. So we are taking a step of 0.1. So this is 0.1. Little steps are good. The previous y value is 1/2. We'll go with the decimal, which is 0.5. H is that delta x, same thing, which is 0.1. And evaluate the function at the previous value. So the previous y value was 0.5. The previous x value was 0. So it's early. I'm not going to attempt mental math this morning. So I've got 0.55. So my new step up on my t value, oh, actually I'm going to call this x. My new x value is 0.2. So my previous y value is 0.55 plus that delta t, or that h, or that delta x in this case, 0.55 minus 0.1. I'm using my calculator off screen here, and I got 0.595. Remember, don't round till the end. As soon as you round, you've introduced a rounding error. So 0.595 plus 0.1, 0.595 minus 0.2. And I got 0.6345. All right, and you just keep going. Now, I hope I don't have any calculator errors this morning, but that's why I like working together in class. We can check each other's answers, but I'm on my own this morning. So if you're working through this video and putting them in your calculator and getting different values, because I messed up somewhere or hit a wrong button, let me know. Send me an email, let me know. Okay, still going. 0.66795 plus 0.1 is 0.66795 minus 0.5 times 0.1 plus 0.66795. My table's not big enough. 684745. All right, one more. Last one, I promise. 0.684745 plus 0.1, 0.684745. I have seen these on the AP exam for sure. Have I seen? Oh, see, I goofed already. Oh, I made a mistake. And the last one. Look at, I put a 0.5 here and it should have been a 0.4. I should have been on the previous line. I wasn't. So I have an error. Now, if you make a mistake in the first step because it's recursive, it copies all the way down, which is not so helpful. Plus 0.66795 makes this 0.694745. 0.694745. 0.694745. All right, so it happens. As I was saying, I have seen these on the AP exam for sure, but not usually with 6 steps, usually with like 2 or 3 steps. And I've seen negative. They'll give you a delta X of a negative value. So that means instead of counting up, you're counting backwards. I've seen that as well. So keep that in mind. 4745. All right, there we go. 0.7142195. Now, I don't have my notes from last year to compare values. They're sitting in my classroom. So I'm assuming that these are correct. Now, before you go, this is Euler's method. So not difficult, maybe a little bit annoying because it's so long, but really not too difficult. All right, recipes, banana bread recipe, my favorite. I want to show you, here we go. Just kind of what it's looking like. I know Wikipedia can't take it for true value, but this is the quickest image I could give you. That blue line would be the actual function, and that red jagged piece, that connected dots piece, that's what Euler's method is doing. So we have that initial value that they gave us here. And then when we have, that next step that's taking us here, and then the next step is here, and the next step is here, and the next step is here. So it's giving you new XY coordinates to connect the dots. Now, obviously, the smaller that step, that H, that delta X, that delta T, the smaller that is, the closer you would be to the original curve. When do we actually need this? Because you have to have the if you have the differential function and not the original function, that's where you would use it. If it's something, a differential equation that you can't solve, if you can't separate the variables and solve it, you could estimate what it looks like with this. It goes hand in hand with slope fields. I kind of sit in the middle of slope fields. So anyway, they're kind of neat. Do the best you can with these. Keep practicing these things. I know this is tough, but you are more than halfway through the material, which is wonderful. So almost to the end of the AB material. All right, have a great day.